This is the last topic in the syllabus, which is solving ordinary differential equations by the technique of separation of variables. So a differential equation that you can write in this form, some function of x plus a function of y, dy dx equals 0. When it's possible to write your differential equation like this, then we say the variables are separated. As a mnemonic, we often write this as m of x dx plus n of y dy equals 0. As if this were a fraction, we can multiply through by it, but then when we integrate. So let me just do some problems. This is the way to learn mathematics, is to solve problems. So suppose we have the equation x squared plus 4 dy dx equals xy. So this is not of this form yet. We could make it in that form as follows. We could divide by x plus 4 times y. We would get 1 over y dy dx equals x over x squared plus 4. If we brought this over on the other side, minus x over x squared plus 4 plus 1 over y dy dx equals 0, this would be m of x, this would be n of y, but there really is no reason to do this. This is the form we want it in. And then we integrate. If you like, I can write 1 over y dy is x over x squared plus 4 dx and integrate. And what we get is what? The integral of 1 over y is log absolute value of y. The integral of this, if I multiply and divide by 2, then this is the natural log of x squared plus 4 plus a constant. Let's see, 1. So if I exponentiate, I get the absolute value of y is x squared plus 4 times e to the c1, or y is plus or minus e to the c1 oops, made a mistake. There's a 1/2 here. 1/2 the log of that. So this is equal to the log of the square root of x squared plus 4 plus c1. This is square root. So e to the c1 square root of x squared plus 4. This is some non-zero constant. Of course, if you let y be the constant function 0, this is also a solution. So the general solution of this differential equation is y is some constant c times the square root of x squared plus 4. So let's just go back and review what we did. Here was the differential equation we started with. Here the variables are not yet separated because I have x and y here and x and y's here. When it's separated, on one side of the equation you only have y's, and on the other side you only have x's. But I can divide. If I divide by y, I bring the y over to the left. If I divide by x squared plus 4, I bring this over to the right. And so now I've just rewritten the equation in this form, and in this form the variables are separated. And I can integrate and solve the equation. And you can check by differentiation that this really is correct. So this is a fundamental technique and is one of the things you're supposed to leave calculus 2 having learned. Let's look at the second example in the text. So in the second example, we're given the differential equation in this form, xy dx plus e to the minus x squared, y squared minus 1 dy equals 0. And we have this x squared and dy. I mean, you should think of this as xy plus e to the minus x squared, y squared minus 1 dy dx equals 0. So this really is the differential equation, but it's written in this what is called differential form. And it's not quite separated, right? It's not separated. Let's try and separate it. So we have e to the minus x squared, y squared minus 1 dy equals minus xy dx. But I only want y's on this side and x's on this side. So if I multiply through by e to the x squared, I get y squared minus 1 dy is minus xy e to the plus x squared dx. And to get rid of this y, I divide by y squared minus 1 over y dy is minus x e to the x squared dx. And then I'm going to integrate. Now I can simplify this. Y squared minus 1 over y, this is the same as y minus 1 over y dy. And minus, let me write this as minus a half times 2 x e to the x squared dx. And I do that on the right because now it's easy to integrate. When I integrate this, I get a half y squared minus log of the absolute value of y equals minus and minus 1/2. And the integral of 2x e to the x squared is e to the plus x squared plus a constant. So if you like, I can write this as y, I can multiply by 2. Y squared is minus the log. This becomes absolute value of y squared, which is just y squared, equals minus e to the x squared plus a constant. Or if you like, y squared minus the log of y squared plus e to the x squared is a constant. So I found y, the solution of this differential equation, implicitly. I can't solve for y, but every solution of the differential equation, every function y that solves the differential equation solves this. But now suppose we also have an initial condition. The condition is that y of 0 equals 1. So we want to find a solution where when x is equal to 0, y is 1. So if you plug in y equals 1 and x equals 0, that'll give us the value of c. This says 1, log of 1 is 0, e to the 0 is 1. 1 plus 1, or 2, is equal to c. So the solution of the differential equation that satisfies this initial condition is y squared minus log y squared plus e to the x squared equals 2. That's the solution. This was example 2. Let's do example 3. So here's the way the problem is expressed in the book, and we have to understand the words and translate it into mathematics. find the equation of the curve that passes through the point 1, 3, and and has slope of y over x squared at every point or any point xy. So what does it mean to say that our function y has slope y over x squared at any point xy? It means that dy dx, the derivative, is y over x squared. And if it goes to the point 1, 3, y evaluated at 1 is equal to 3. Now, this differential equation is separable. I can separate the variables. I can write this as 1 over y dy dx equals 1 over x squared. Or, if you like, 1 over y dy is dx over 1 over x squared. And then I integrate. So I get the log of absolute value of y is minus 1 over x plus a constant. If I let y equal to 1, the log of the absolute value of 1, which is 0, is, sorry, if I let y equal 3, and x equal 1, the log of 3 is minus 1 over 1, minus 1 plus c. So c is equal to 1 plus log 3. That gives me the value of my constant. See, when x is equal to 1, log 3. So log y is minus 1 over x plus c. If I exponentiate absolute value of y is e to the minus 1 over x times e to the c. And this is always positive, so I'll just write this as y. Sorry. If you go through the point 1, 3, when y is equal to, when x is equal to 1, y is equal to 3. So e to the c is 3e. So c is equal to 3, that's log 3, plus 1, just what I got over here. That's perfectly okay. So if I plug this value in for c, this is equal to e to the c, e to the 1 plus log 3, e to the minus 1 over x, e to the log 3 is 3 times e to the 1 minus 1 over x, or 3, if you like, e to the x minus 1 over x. So the solution of the differential equation is this. Yeah. So the homework for this section was 6.3, 1 to 17 odd. So let me just do one or two of them. Start with number 1. Solve the differential equation dy dx equals x over y. We can separate the variables, just multiply by y. Y dy dx equals x. Or, if you like, y dy equals x dx. The y's are here, the x's are here. Integrate. You get a half y squared is a half x squared plus a constant. Y squared equals x squared plus 2 times the constant, which is just a constant. So y is plus or minus the square root of x squared plus c. That's the solution. This is number 1. What about number 15? We have the differential equation y prime minus 2e to the x equals 0, and the initial condition y at 0 is equal to 3. So we can write this as y dy dx equals 2e to the x, or y dy equals 2e to the x dx, and integrate. You get 1/2 y squared is 2e to the x plus c, or y squared is 4e to the x plus a constant. If you plug in x equals 0, y equals 3, we get 9, which is 3 squared, is 4e to the 0 plus c. E to the 0 is 1, is 4 plus c. So c is equal to 5. So y squared is 4e to the x plus 5, or y is plus or minus the square root of 4e to the x plus 5. That's the solution of that differential equation. And I'll do more in the problem sessions if there are questions.